Hello and welcome to the next of the lectures in this series titled Approximate Reasoning Using Fuzzy Set Theory, a course offered over the NPTEL platform. In the last lecture, we began to see how to construct fuzzy implications from other fuzzy logic connectives. Specifically, we have seen how to build SN implications, the family of SN implications from a given T conorm and a negation. In this lecture, we will have a general introduction to another family, perhaps a very important family of fuzzy implications known as the R implications. A quick recap of the family of SN implications. We have seen that the truth table for the classical implication can also be captured by this formula, which is also called the material implication. P implies Q is given as negation P or Q. That means P implies Q is true, either if P is false or Q is true. Taking Q from this, we define the family of SN implications. Given a T conorm S and a fuzzy negation N, we defined a function I as S of nx, 1, y. We denoted it by ISN, the SNN standing for the T conorm S and negation N, to indicate that this implication is coming from the family of SN implications. We have seen that every such function ISN is a fuzzy implication, and we have also seen that many of the basic fuzzy implications do belong to this family. Then we went on to discuss what desirable properties SN implications satisfy. The first of them is the left neutrality property, or just simply the neutrality property, which says that I of 1, y should be equal to y. We have seen that this property is held by all SN implications. The next property is that of the identity principle. We have seen that not all SN implications satisfy this property. Similarly is the case with ordering principle. Not all SN implications satisfy this. However, the exchange principle is indeed satisfied by all SN implications. We have seen this is largely due to the fact that a T conorm is both commutative and associative. It is from there we are inheriting, based on the definition of an SN implication, that all of them do satisfy the exchange principle. Now let's move on to the second family of fuzzy implications, that of R implications. Well, the second family of implications, and perhaps arguably the most important family of fuzzy implication, is called the R implication. These have had varied origins, but perhaps a good way to introduce them is to look at some correspondence between logic and set theory. We know that in the classical setting, the classical logical operations are related to corresponding set theoretic operations. For example, the meet in the Boolean algebra is in fact related to the intersection in terms of the corresponding subsets of the power set of corresponding subsets of the universal set X. So we can always relate a classical logic operator to another equivalent fuzzy set theoretic operator. If you ask about the implication, what could it be related to? Perhaps it could be related to the subsethood operation. How so? Now let's look at this. Once again, a very familiar conditional by now. If f is differentiable, then f is continuous. We know for sure that this conditional is valid. Now what it seems to say is this, that the set of differentiable functions is actually contained in the set of continuous functions. That's what we are claiming here. Because if you take an f, if it is differentiable, it is also continuous. So if you consider a set of all differentiable functions, then it is contained in the set of all continuous functions. But implication is not just subsethood. For instance, look at this formula. P implies Q. We have related it as, or equivalently written it as negation P or Q. So now when you are looking at when is this conditional true, it is not only required that whenever P is true, Q is true, but even when P is not true, it becomes true. That means if P is false, then the conditional doesn't come into picture. The antecedent is no more true, so the conditional doesn't come into picture. So you see that negation P or Q captures this fact and says that whenever P does not happen, it's still the conditional is valid. Whereas in the case of subsethood, we want that A is subset of B if and only if every X in A also belongs to B. It does not talk about when X does not belong to A. So if A does not belong to A, then it may well belong to B or not, and that's what this conditional is capturing extra. Well, now in terms of set theoretic operations, if you were to look at it, we could also write this from our previous knowledge that when you look at it from Boolean algebra point of view, P of X with the usual intersection, union and complementation, they form a Boolean algebra. So from that point of view, you could write also this implication in some sense as A complement union B. And this is what we have captured in coming up with the family of SN implications. Now, we could also write an equivalent formula like this. Now, this needs a little bit more explanation. Let's look at it. What does it say? It says A implies B can be expressed as union of all those subsets C of X, where X is the universal set, such that A intersection C is contained in B. Let's look at this from a Venn diagram point of view. So this is my universal set X. Now, this is my A, and let this be my B. So this is my A, this is my B. If you go by this first formula, A implies B is equivalent to A complement union B. Essentially, A complement contains everybody outside of A. Union B, that is this. So the only part that is not considered in this is this part. I'll just shade this with some other color. So essentially this is the part that is not considered. So you could also write A implies B is equal to A complement union B as, first remove B from A, that is what this part is, and take the complement. So the parts marked in this orange or red color, they are the ones that are not part of A implies B. Now, what does this formula tell us? Let's look at it. Once again, this is X. This is A. This is B. It tells us take a C, which is a subset of X, and look at A intersection C. Is it contained in B? So let's look at this S or C. Now, what is A in this S or C? What is A intersection C? Really this part. Now, is this contained in B? Yes, it is contained in B. So this C actually could be considered in this family here. Now, we want not just some C, but we want the union of all of them. So essentially we are asking for the largest such C. Do we have any other C like this? Yes, let's look at this. Another C. So this is another C. Now A intersection C will be this. But unfortunately, if you look at A intersection C, it is not completely contained in B. So this C is practically useless for us. It will not fall into this set here. What about this C? A intersection C is empty, but empty set belongs to any other set, a non-empty set. So that means this C also can be considered. Now the question is, how do we find the largest set C? Well, consider this fellow. We said that this C will belong here. What about this C? Look at his intersection. The intersection with A is this, which is contained in B. So now we can try to blow this C a little further. Why not consider it like this? So take this all the way here and then bring it here. So now if you consider this C, the intersection still remains the same. So from here you get an idea what could be the biggest C that we can draw. Clearly, it would look something like this. Take this fellow. All of them. So this is one C that could look very nice, but still we are missing all these things. Why not take all of them? So now when you consider from that point of view, you actually see that the biggest such C is essentially that which covers everything outside of this. So if you consider this to be the set D, then the biggest set C is essentially D complement. But what is D? It is essentially A minus B. So you see here, from set theoretic point of view, we have actually got another way of looking at implications or the conditions. Now, because we do have an idea that the set of all subsets of an X, if you consider it from an algebraic point of view, you get a Boolean algebra, a Boolean lattice. So now, writing this in terms of the lattice operations would mean like this. So P implies Q is the supremum of all those T less than or equal to 1. Remember, this is a bounded lattice where X is the topmost element. Supremum over all those T less than or equal to 1 such that P meet T is smaller than Q. This is essentially exact transliteration of this formula from the setting of set theory to that of the lattice theory. So it's only a change in language. So now you have one definition here of P implies Q as negation P of Q. Now we have another definition here. In the case of classical logic, when you had only two truth values 0 or 1, both these definitions are in fact equivalent, as you can see from the corresponding truth table. However, in the case of fuzzy logic connectives, in the setting of fuzzy logic, they are actually quite different. And what do we mean by that? Well, let's look ahead. So now this is the formula that we want, and the only operation that we seem to be using is that of a mean, which we know can be captured quite nicely in terms of T norms. So let's begin with the T norm T and translate this formula as follows. So supremum over all those T element of 0, 1 such that T of x comma T is less than or equal to y. This T is actually coming from 0, 1 interval, which is our set under consideration. So if you define a function it from T like this, what can be shown? It can be shown that it is always a fuzzy implication. That is, it is decreasing in the first variable, increasing in the second variable, and satisfies all the boundary conditions. This can be seen without much difficulty. If we consider the sets, we will see how to look at this when we discuss some properties. Perhaps from there you may be able to easily prove it to yourself that indeed this formula does give a fuzzy implication. Okay, if you consider the usual T norms, what is the kind of R implications do we get? Let's consider the minimum T norm. And let's look at what is the corresponding R implication we get from this. Remember, it is defined as supremum of t element of 0, 1 such that t of x comma t is less than or equal to y. Now if you put m here, then you put tm here. So writing this formula like this, supremum over t element of 0, 1 such that mean of x comma t is less than or equal to y. So to help us in this, for a fixed x comma y, let's call this set A of x y as set of all those t element of 0, 1 such that mean of x comma t is less than or equal to y. And essentially ITM of xy will be the supremum of this set. First of all, we should see in general how would this set look like for any t. That is, if I remove mean here and put just t, the first question is AXY equal to NT for some x comma y. Now, this never happens for the simple reason, look at this, 0 will always be element of AXI for any XY element of 0. Why so? Because look at this, t of x comma 0 is equal to 0 and less than or equal to y for any y, which means 0 always belongs to AXY. And not only this, there are many other interesting facts about this set AXY. Now what can this AXY be? If t belongs to AXY, then we can say that any t dash smaller than t also, for t dash element we have t dash belonging to AXY. Then how do we prove this? Note that if t belongs to AXY implies t of x comma t is less than or equal to y. However, we know that t dash is smaller than t. That means by monotonicity of t, the t naught t, we know that t of x comma t dash is smaller than or equal to t of x comma t, which is less than or equal to y. That means this implies t dash also belongs to AXY. So essentially what we have is, if you look at it like this, you have an x, you have a y. Now you are looking at AXY for this x and y. X and y can be whichever way, x can be smaller than y or greater than y. But we know 0, 1 is a chain, so both given any two elements, they are related under the ordering. So if we know that this t here is such that t of xt is less than or equal to y, then essentially the entire interval also belongs. That means the entire interval is also contained in AXY. So it can be shown, we will see with some examples soon enough, that AXY typically looks like this. For some t naught, either it is 0 comma t naught, or for some t naught it is close to 0 open t naught. So essentially AXY is never empty. Okay, so now let's come back to ITM of XY, which is nothing but supremum of t element of 0, 1 such that minimum of x comma t is less than or equal to y. Then, how would this look like? To understand this, let's split the case. As was mentioned just now, let's take xy element of 0, 1. Now we have two cases. Case 1, x could be less than or equal to y, or x can be greater than or equal to y. Let's look at this. X is less than or equal to y. So that means let's assume that x is here and y is here. Now, if I take a t here, what happens to min of x comma t? Min of x comma t, t is smaller than x, so this is equal to t, but it is less than x, and so it is less than y2. So definitely this t will belong to axy. So this t belongs to axy. Now what if I take a t here or a t dash here? Once again, minimum of x comma t dash is actually equal to x, because t dash is greater than this, but x is smaller than or equal to y, so that means minimum of x comma t dash is less than or equal to y, which means once again t dash also belongs to axy. What if I take a t double dash which is bigger than y also? Now if we look at it, minimum of x comma t double dash, once again t double dash is bigger than x, which means min of x comma t double dash is actually equal to x, which is still less than or equal to y, because that's the case that we are discussing, which means t double dash belongs to axy. Now how far can we go here is the question. Now t dash, we can actually push it till 1. Why? Because look at this, minimum of x comma 1 is actually equal to x, and in this case it's always under the assumption that we have x is less than or equal to y, which means 1 also belongs to axy. But we know that if a t belongs to axy, then everybody below t also belongs to xy. This implies axy in this case is the entire interval 0, 1. Now what is ITM of x comma y? It's nothing but supremum of axy, which is nothing but supremum of 0, 1, which is from our understanding of lattices with respect to the usual ordering on 0, 1, this is actually equal to 1. Now let's consider the second case, x greater than y. What happens in this case? Once again, we need to discuss axy. Axy is set of all t element of 0, 1 such that min of x comma t is less than or equal to 1. And note that x is strictly greater than y here. We can ask the same question now. 0, 1. Now y is here and x is here. Can I have t to be somewhere close to 1? What if t is actually equal to 1? Then we see that min of x comma 1 is equal to x, but it is greater than y under the assumption that we have. So t is equal to 1 is not going to work. Then what would work for us? What if t comes close to x, or what if t is actually equal to x? If t is equal to x, we see that min of x comma t is min of x comma x, which is greater than y. So clearly any t greater than x is not going to work. But what if t is between y and x? Once again we see that min of x comma t may be t, but this t is greater than y. This implies for this t, I'll put it as t dash does not belong to axy. So if my t dash is here, it is not going to work. How much closer or lower should I need to come towards 0 so that t dash or t can actually belong to xy? It is clear that I can come only till y. What if my t is equal to y? Well, minimum of x comma t is now t, because t is equal to y and y is actually smaller than x. Y is smaller than x. This implies, I probably put this as t double dash. T double dash belongs to axy. Now we know that the moment a particular value of t belongs to xy, every value of t or every value below that, so the entire interval 0 t double dash actually will belong to axy. What if my t, I take t triple dash as some y plus epsilon? That means it's just marginally above y. Now if you look at this, this is min of x comma t triple dash is equal to, it is still smaller than x, so it is t triple dash, which is y plus epsilon. Now, since epsilon is definitely greater than 0, however small it may be, is greater than y, this implies that t triple dash does not belong to axy. Yeah. So now, that means if you look at axy, we see that this is nothing but the interval 0, y and y included. So in this case, itm of x, y is supremum of axy. This turns out to be supremum of 0, y is equal to y. So from this, we get the formula that it is 1 if x is less than or equal to y, and it is y if x is greater than y. Now we know that it's essentially the Gödel implication that we have. So far, we have given a gentle introduction to the family of R implications. We have seen the formula itself is inspired from sec-theoretic equivalence between the implication, the conditional that we have represented as negation P or Q. We introduced it as A complement union B, and then from there we saw how you could look at it as finding the largest subset C whose intersection with A is contained in B. We have seen how to obtain the R implication for a particular T-norm, that of the minimum T-norm. In the next lecture, we will look at obtaining the formula for yet another R implication from another T-norm, perhaps the product T-norm. And then we will discuss the properties the family of R implications does possess vis-a-vis the identity principle, ordering property, the exchange principle, and the neutrality property. And finally, we will also do a similar study of yet another family of fuzzy implications called the QL implications, which are quite interesting in that they are actually obtained from all the three other fuzzy logic connectives that we have seen, that of a T-conorm, T-norm, and a negation. In the next lecture, we will deal with these, and with that, we will come to the end of constructing fuzzy implications from other fuzzy logic connectives. As was mentioned already, there are many other ways of obtaining fuzzy implications, but we will restrict ourselves only to these three families in this lecture series. Once again, a good resource for looking into for the topics that we have covered in this lecture is the book on fuzzy implications. Glad that you could join us today for this lecture, and looking forward to meeting you again in the next lecture. Thank you once again.